Okay, let's have a look at some harder sine rule questions. Remembering the formulas that we have here, we have a divided by sine A equals b divided by sine B. We can use the sine rule written this way if we want to find a side length. It just makes the solving a little bit easier. Let's just do a quick recap of what the sine rule means. So here, the a divided by sine A refers to an angle side pair. So we see that side A appears opposite angle A, and then side B appears opposite side angle B. So to use the sine rule, we must know one side angle pair. Then what we can do, for instance, if we know B, we can find the side length opposite B. To solve for an angle, we can use the formula written as sine A on A equals sine B on B. Remember here that if you solve on your calculator will always give you an acute angle for A. However, if the angle is obtuse, to find that we need to do the calculation 180 degrees subtract A to give us an obtuse answer. This is called the ambiguous case of the sine rule. Here is the first problem. Pause it now if you'd like to have a go at doing this yourself. The first thing I'll do here is dot in the road. The house is first seen at a bearing of north 15 degrees east. I'll now show that information. And I'll put in my house. Now the car drives along from this position north until the bearing of the house changes to north 50 degrees east. I think this location here would approximately show that. And that distance was 800 metres. Now the question wants me to find the shortest distance from the house to the road, which is this one, which makes an angle of 90 degrees to the north-south road. So this distance here that I want to find D is an east-west line. Now the only distance I'm given is this 800 metres, and that's not going to be useful to find D because it's not part of a triangle with D in it. So let's work with a triangle first that involves this 800 metres. I see now in this triangle I know 15 degrees and 800 metres. That's not enough to solve yet, but I can see up here that this angle must be 130 degrees. And if we know two angles in a triangle, we know all three. Now I'm going to use the sine rule to solve for this side length, x. So let's write that out. Okay, so I need to work in side angle pairs. So x divided by sine 15 equals 800 divided by sine 35. Multiplying through by sine 15, I get this expression, which gives me 360.99 metres. Now I can go ahead and find D because it is now in a right angled triangle where I know the 50 degree angle and the side length x. So using my right angled trigonometry, I see that x is my hypotenuse and D is opposite. So I'm going to use sine theta. So sine 50 degrees equals my opposite side D divided by my hypotenuse, 360.99. Rearranging, I get the distance as being 277 metres to the nearest metre. Here is the second question. Pause now if you'd like to have a go at it. Now the question stated find the two possible values of A. I'll come back to that later. Let's just have a look at the triangle I've drawn here. Firstly, we see that I have a side angle pair, so I can use the sine rule. But here I see I can use the sine rule to solve for angle theta. That's not going to help me straight away. However, I will then know two angles in a triangle, and I can find the third, and then I'll be able to use the sine rule again to find A. So let's do the first step of finding theta. So I want to find theta, so I write down sine theta divided by 9.3, so my angle side pair, equals sine 39 degrees divided by 7.3, my other angle side pair. Now to solve for theta, my first step is to times by 9.3 and punching that into my calculator. Now using the inverse sine. Now I can solve for the angle I've just labelled as A. Now I can find length A using the sine rule. So A divided by sine of the angle opposite equals 7.3 divided by sine 39, my other side angle pair. Now I'll multiply both sides by sine 87.7 and I'll get 11.59. Now we need to talk about why there's another possible answer of A if we consider the information that we're given. So let's redraw the triangle again. So this is what the triangle looked like initially. So we see a 39-degree angle here, and one of the side lengths that makes up that 39-degree angle has a length of 9.3 meters. Let's just rub out the 7.3 for now, and we'll draw it back in a second. So this other side length down here, we don't know the length of that. So if we just dot that off, it has some length that we're not too sure about yet. But what we do know is that the side opposite has a length of 7.3 meters. So the side we're going to draw in here. However, there's two different positions we can draw that length in. We could draw the 7.3 down here, or we could draw the 7.3 in this direction. So both of them, those sides have the same length of 7.3 meters. But I see I have two different triangles using the same information. We just solved the problem for A being this length here in the big triangle I've formed. However, there's another solution for A in this second triangle that I've formed. Now let's have a look at how those two solutions relate to each other. In the larger triangle, we solved for this angle here, theta, before, and we found that was 53.3. As we've got an isosceles triangle here, the two equal lengths obtend the same angle. So this angle in here is 53.3 degrees. So this angle in here is given by, this is the ambiguous case of the sine rule. So the angle you get in your calculator, if we just blindly solve, will be the acute one. However, if the triangle that we've drawn clearly shows an obtuse angle, to find that one you need to go 180 degrees, take away the angle you get given in your calculator to find the obtuse angle. To find the other possible value of A, we go through the same system. First, we need to calculate the angle opposite A. Then we use the sine rule to find side A. So A, the side we want to find, divided by sine of the angle opposite, is equal to 7.3 divided by sine of the angle opposite. Now solving this gives us 2.87 meters. So our two solutions are 2.87 meters or 11.59 meters. Here is our last question. Pause now if you'd like to have a go. Now in this question, getting the diagram right is the tricky bit. First I'll put in the slope, which is at 10 degrees to the horizontal, and the tree is at the bottom of this slope. Now from a point 30 meters up on the hill, the tree is observed at an angle of elevation of 25 degrees. So here we have our 30 meters up the slope, and the angle of elevation to the tree is always measured from the horizontal. So here I'm drawing in how the tree is observed. So above the horizontal we have 25 degrees. So we'll see here in the large triangle at the moment, the height of the tree, up the slope, and the line of sight, we don't yet have this full angle in here. However, if we look at our 10 degrees, that's an angle from the horizontal. Up here at this point we have a horizontal as well, so this is the angle of depression, and this is an angle of elevation, and they're equal. So I can add in 10 degrees in here. So my overall angle is 35 degrees at this point. It still doesn't look like enough, so we'll look for some more angles because we definitely can't find lengths easily. This angle in here is going to be 90 degrees, take the 10, so that is 80 degrees. Now I know two angles in my triangle, so I can calculate the third, 65 degrees. Okay, so we want to find the height of the triangle, so we want to find its distance. So if we're going to use the sine rule, we must know the angle opposite, which we do. We do know the 30 meters, and we know the angle opposite that. So here's my side angle pair, and another side angle pair where I want to find one of the values. So I can go ahead and use my sine rule. So h, the height of the tree, divided by sine of the angle opposite, equals 30 meters divided by sine of the angle opposite, and solving for h gives me 19 meters to 1 decimal place.